To get to give this talk. My goal today is to give you kind of a heuristic feel for what we see in the microwave background. And I'm going to sketch out a little bit about how we actually do the calculation rigorously. But what I mostly want to do is give you an intuition about what we see in the microwave background, how it depends on the composition of the universe. And I'm going to try to do this in a way that I think those of you who may have heard talks on this before will be different. I'm going to try to look at things mostly in real space rather than Fourier space, and I'm going to focus on polarization fluctuations more than temperature fluctuations. Because as you see, they're actually simpler in their behavior, and our data got good because temperature fluctuations are bigger, got good on temperature fluctuations first, so that's usually what we talk about when we introduce it. I'll come back to temperature, but I'm going to try to tell the story in a different way, and actually in a way in which I've never spoken on before, so this will be an experiment. So we're going to start with thinking about first the homogeneous universe, what's going on to the universe during the epoch at which microwave background fluctuations are primarily generated, redshifts of around 1,000. And as Marlene talked about earlier, you're basically just after the transition from radiation domination to matter domination. So the large-scale evolution of the universe is governed by the Friedmann equation. And I should put a 4 here, so I can write it as A equality over A to the 4th. There's a radiation component and a matter component. And exactly when this transition takes place, which you'll see will have an impact on the evolution of the dark matter in the microwave background, is going to depend on the energy density in radiation and the energy density in matter. The energy density in radiation is 2 components. The energy density in photons, that we know very well. We know the microwave background temperature to about a part in 10 to the 4, plus the energy in relativistic species. And that includes the energy density in neutrinos, and depends on but also depends on anything else created in the early universe. Right? So the early universe is a very good accelerator. If there are any light particles that are stable, created any time in the history of the universe, they're still there. So this, historically, I find I've gotten asked by string theory colleagues about every couple years. Someone comes into my office and says, what if the universe is symmetric and there's an identical sector to ours? How would we know? One way we would know is this equation counts everything in the universe. So if there's other degrees of freedom, other light particles around, it would show up in how the universe expands. And as you'll see, the evolution of H with as the universe expands is one of the basic things that enters into all of our equations. It gives us our length scales. It gives us our dynamics.
Does this depend on the spin of the particle?
Does it depend on the spin? Well, if you're looking at a fermion or a boson, high spin, you just count up how it contributes to the energy density. This is just gravity. It's just, how it couples. You can think of this as we start with the Einstein. You derive this equation by starting with the Einstein equations and then assuming the uniform Robertson-Walker solution for the homogeneous equation gives you the Friedmann equation. So you just sum up whatever's there in the universe.
So this assumes Einstein gravity.
This assumes Einstein gravity. Now, one of the things I will show you later in the talk is we have a very nice and simple test of a requirement on alternative gravity theories in terms of what they need to do to reproduce the observations. So that's one part of the story I want to tell. So in addition to keeping track of the universe's expansion rate, we need, if we want interested in the microwave background, to keep track of the ionization state of the universe. This will be my heuristic side. And the key reaction going on is electrons and protons are combining to make hydrogen, and the microwave background, which is then much hotter, is ionizing the hydrogen. And this is in equilibrium. And an approximate way of thinking of the evolution of the universe is you very rapidly go around redshift of 1100, redshifting, Z increasing this way, so this is going to a hotter early universe, from being nearly fully ionized to nearly fully neutral. And the ionization state drops to about 10 to the minus 4. Now, to do this properly, we have to keep track of recombination, keep track of all the different states. What plays an important role in this is the fact that you recombine to 2s and then you have to have a 2-photon process to get to 1s. Today, when we do the calculation of the evolution of this ionization fraction, we need to do this right at better than the 10th of a percent level. So you need to keep track of all the states of hydrogen up above n equals 100, but it's all known physics. You just write this down and solve this on the computer and fit this, and that plugs into all of our calculations.
What did you get your answers?
Oh, greater than 100.
Really?
Yeah. Yeah. So if you, there's some nice papers on this by Jens Trubla, GLC, if you're interested in looking at this, and Yassine Ali Hamoud, which I may or may not have written properly. I think that's the right spelling. But these are two recent papers to look at the recombination physics. This of course means if you do anything to change the value of alpha at redshift of 1100, it propagates through and changes the details here, and we'll have observational effects.
Give a test on alternative theories.
On alternative theories of
Well, you said
of gravity?
You said alternative theories have a certain requirement. You were explaining it.
I'm not there yet. It's 10:10. Give me, how much time do I have to lecture? An hour?
An hour now and half hour later.
Okay. Sometime before the break, I should get to it. But for now, it's Einstein gravity. The laws of physics in the early universe are the same as the laws today. Those of you who were here yesterday, there was that nice list Marleta made of here's what we assume. I'm making those same assumptions. We'll play with them a little bit, but until you hear later, it's Einstein gravity. Now, it's interesting just to think quickly about why is this at redshift of 1100? Redshift of 1100 corresponds to a temperature of about 3,000 Kelvin. That corresponds to about a third of a EV, right? The binding energy of hydrogen is 13.6 eV. Why is it 1/40th of the temperature where you think it would be at? That's because we have so many photons around, right? There's more than 10 to the 9 photons per hydrogen atom. So you get to be way out in the Wien tail of the distribution and have photons way out in the Wien tail ionize things. So roughly speaking, this transition is at about 13.6 dividons per hydrogen atom. So, and the fact that you're so far out in the log means this happens really quickly, because you go from, here, you're 36 e-folds out, and there's more than enough photons. Here, you're 44 e-folds out, and e to the minus 44 is much smaller than e to the minus 36, and you very rapidly go through this transition of being fully ionized to fully neutral. That also means that the surface of last scatter, where we see the photons coming from, is rather thin. The dominant process to govern the propagation of photons is just Thomson scattering. Right? Just you have all those free electrons, things just scatter. And when we look out at the microwave background, and I think of myself as, the telescopes looking out in space back in time, what we care about is what is the optical depth? What is the probability of the photon colliding with an electron? That optical depth is just NE sigma t times c as we look back. And when I look at a photon and I ask what's the probability of it coming from a given redshift, that probability is the visibility function, which is d tau dz, the probability of having a collision in that given redshift, weighted by e to the minus tau. And this function is pretty steep, pretty peaked at redshift of 1100. So most of the photons we see are coming from between redshift of about 1150 and 1050. The effective thickness is less than 100 in redshift. That lets us make the approximation, if we're just thinking about the physics of what's going on, of the universe being completely ionized at high redshift, the optical depth being very large, so that the electrons and photons are coupled together. So we talk about, and the electrons and protons coupled together in a baryon photon fluid. I'm saying protons, but there's also helium ions around at the time, and one needs to include that to get the proper answers, but the physics is all the same. So you've got, at this early redshift, a coupled baryon photon fluid. And at this point, this is the surface of last scatter. We'll call that Z star. The photons propagate freely from here to us. Now, there's some small corrections. There are some free electrons around. Later, around redshift of 10, stars form. They reionize the universe. That will affect things at the few percent level. We need to keep track of that to do things properly. But you can, to leading order, think about observations of the microwave background as measuring fluctuations on this surface.
Why do you pick up a baryon photon fluid rather than electron photon fluid?
Because electrons and protons are coupled by the electric force. Right? If you move electrons relative to protons, you very quickly create a very strong electric field. The strength of electromagnetism is so much stronger than gravity that the time scale for correcting that is tiny. You can really view it as a single fluid. Proton, and there's some very subtle, there's some subtle things that you can take advantage of it, the protons responding a little differently than electrons at certain times, but except for some very small correction, you should think of this as a single fluid. Now, it's, of course, a single fluid of protons, electrons, and photons.
Yeah, that's why I'm asking why do you say baryon photon rather than electron proton?
Because you also have helium.
Okay.
I guess it might be important to point out that cosmologists say baryons, and they really mean everything in a standard model because fermions have such a small mass.
Yeah.
That if you count them
I
out-
see.
So it's baron helium photon fluid.
Yeah. So cosmologists call
It's a
electron baryons?
Yeah.
we call it, well,
I mean,
We-
if you're counting the mass, if people say omega baryon, the fraction
of electrons.
is so tiny that
It's a mega proton plus a mega electron. We know that there's charge neutrality in the universe, so every time there's a proton, there's an electron. So we don't track those separately because they're trivially related. So you can just think of this as this.
say baryon
But they say baryon, we're specific. But we say baryon fluid, we mean a fluid that's a protons, electrons, helium, all moving together, tightly coupled. And yeah, so then things will propagate from here to there. So what we do when we actually do the calculations is we actually don't treat this as a fully coupled fluid. We keep track of the evolution of the universe. We write down the metric. We do linear perturbations. We write down the distribution function for the photons. The photon collision times are short enough that it's well represented by a thermal distribution. So the perturbations in the distribution are perturbations in the temperature of the universe. So we view photon fluctuations as only fluctuations in temperature. And we write down a Boltzmann equation coupling the photons to the electrons, evolved that together with linear gravity. And there are, if you hear people talking about results from various computer codes like CMB-FAST or CLASS or CAM, they're all solving, these coupled equations. And all these codes, by the way, are very easy to run. They're all available online. If you ever want to play with them, you can just download CLASS and stick in parameters and CMB spectrum come out. And if I was teaching this as a class for students, one of the first assignments is, you download the code, you give me graphs with different plots, and change the physics like adding the number of neutrinos, and the exercise to do is do something like increase the number of neutrino species, see what happens here in the code, do the calculation here, and then see what happens to the evolution of the fluctuations in the sort of rough picture I'll be telling you over in the rest of the talk here. And at the kind of rough picture I'm going to sketch here of treating it as a fully coupled fluid, behaving as sound waves and so on, gives about the right answer at the 5% level. That's about the accuracy at which you can do things, ignoring the details. The observations now have gotten so good, we have to work hard and do calculations at 0.1% level. And that's sort of what the demand is, on the theorists who are involved in making sure we capture all the physics correctly. So that means while we do these things to linear order, we have checked the things to second order, and the second order corrections are all small, except for gravitational lensing, which I may get to in the second half if there's enough time. That's the only interesting nonlinear correction that changes things.
The corrections from later periods are also negligible, like from star formation?
Star formation has the effect of changing the optical depth. Yeah. And that's an interesting correction. And we have to, in principle, if we understood the physics of star formation, the basic model would have 5 parameters in it. And we could predict the star formation optical depth due to stars. We don't understand star formation well enough, so we just carry the one probability that photons scatter off of this, and that has the effect of suppressing the amplitude of fluctuations. So we need to include that as an additional parameter. All right, so since we have a fluid, we can write down the equations for a fluid. So basically, the coupled, the fluid equations, mass conservation, momentum conservation, So this is the equations describing the evolution of our baryon photon fluid. And I want people to note that dark matter only comes in here. It only comes in here. That's the only, through its gravitational effects. If dark matter interacted with baryons, and we have strong constraints on that because it would change the appearance of the fluctuations, it could couple here. And because the perturbations are small, we get to do linear perturbation theory. When we do that, these basically are the equations of sound waves. What we need to do the calculation correctly, this is in the Newtonian limit, because we're interested in perturbations on scales large enough that they're comparable to the horizon. We need to do this relativistically, but that's just doing linear perturbation theory in GR. So you just have to carry around perturbations in the metric that affect things. So that this equation, see if we were to linearize this, where's my eraser? Right, this linearizes to delta dot. Let's write this in plus k times v equals 0. If we take these modes, expand them out in Fourier space. If we want to be fully relativistic, we need to keep track of metric fluctuations, right? So that as you climb in and out of potential wells, that changes the temperature of the photons. And that's all.
So the V here is the V of the
Velocity of the baryon photon fluid.
Okay, and so the dark matter has its own V, but since it has no pressure,
Right.
you don't have an
So
equation for it.
you can, right, and the evolution of the dark matter, which I'll get to in about 15, 20 minutes, depends on how quickly I go, is very simple as a result. Because it's just a non-interacting fluid with fluctuations growing under gravity. The interesting behavior is in the baryons, and that's because there's a sound speed. Right? And this term in linear perturbation theory goes as the sound speed times delta. The sound speed is going to depend on the pressure in the photons plus the pressure in the electrons, technically plus pressure in the ions, divided by the density in the photons, the density in the ions. This term's unimportant. These terms are unimportant. So the sound speed depends on you divide through here, it's going to be 1/3 times a term that goes as the baryon to photon ratio. And this is one of the reasons why we can measure the baryon photon ratio accurately, because all the evolution of these fluctuations basically depends on the sound speed. It's straightforward to think about the evolution of the fluctuations. We can actually do an experiment in this room to see what happens when we create a region of excess pressure. You generate a sound wave. Sound wave propagates out. So we have in the early universe primarily adiabatic fluctuations. What that means is we start with regions in which if there's excess amounts of dark matter, there's also excess amounts of universe is uniform. What varies is the overall density. So we'll start with an overdensity in cold dark matter and an overdensity in baryons and photons. And look at how this evolves. I'm solving for the Green's function by chalk and relying on my powerful artistic abilities to convey the evolution. The dark matter evolution is really straightforward. It's cold dark matter. That means it has zero velocity. It basically stays there. So the dark matter perturbation stays there. The interesting thing is the baryons and photons. And the proton, this fluid propagates out, and it moves out and creates a sound wave that propagates out at the sound speed. And it's going to continue propagating until redshift of 1100. And one of the key distances is the sound horizon distance, which is how far it propagates from the beginning of the universe. Z equals infinity to 1100. Oh, it's actually, yeah. We can think of this as from when the fluctuations are generated. And, before they're baryons, as long as it's responding as it's a photon, it's a fluid that's a relativistic fluid. It's moving at, if I had a universe that was, had no baryon number, it would be moving as a fluid with a fully relativistic fluid. It would move at a speed of 1/3. This integral is completely dominated by redshifts of 10,000 to 1,000. So it actually doesn't matter what you do at higher redshift. That's actually important if we go back to some of the things Adam Riess talked about, which I'll just mention briefly. So this is the sound horizon distance. This is the sound speed. This is the cosmic ruler that we use for doing almost all of our measurements. When we look at the fluctuations on the microwave sky, there's a characteristic angular scale associated with the fluctuations. That angular scale is the distance the sound waves moves projected to us. So we then have to what we measure is an angle, which is the sound horizon distance divided by the distance to the surface of last scatter, assuming the universe is flat, which we have a bunch of ways of looking at. And that distance we integrate from now to back to then, and that's the size subtended by in a given size fluctuation. So this says if you want to do something to change the model, change the Hubble constant, that you infer from measuring this angle, you either need to change late time physics, and this integral is dominated by the low redshift end, so you have to change the behavior of the universe recently, or you have to change early time physics. And early time physics here means between redshifts of 1,000 to 10,000 is about where you have to change things for it to matter. So this angle is about a degree. So when you look at, you've seen plots of the CMB spectrum, and that's the position of the first peak.
The redshift of 10,000 is after radiation equality.
1100 is when we make the transition from fully ionized to neutral. 11,000.
No, he's asking where the 10,000 limit on RS. When you said RS is dominated.
Oh, where the 10,000 is? Oh, it's just log. It's getting equal. If you look at the integral, most of it's coming not so much. Matter radiation equality is about 2,500. If you look at the integral, less than 10% of it's coming from above 10,000. So it's
after 1100, right?
Mm-hmm. But what the effects of star formation and later ionization is just to smooth the fluctuations. It doesn't change the angular scale.
Why is the angle at the first peak? Can one understand that?
Yes.
I mean,
Yes. No. And I will, and I will explain it, but I wanted to get to that after a bit later. But I will actually derive the spectrum and why you get the multiple peaks. First, to understand this picture where it's a sound wave moving out that's thin, assumes that the photons and electrons are very tightly coupled. But this transition and this optical depth is finite. So the photons can diffuse relative to the electrons. And the effects you have is, you can think of this, if this is an overdensity, it is. This is a hot region. You have more photons. As this propagates out, this is a hot ring. When you hot stuff surrounded by cold stuff, it diffuses. So the photons diffuse out of the hot regions, so that if I were to look at a cross-section of this, this has a finite thickness, and the thickness is set by how far photons can diffuse out of a hot spot. And that's called the silk damping length. And that's a second scale that will show up in the spectrum, is from diffusion. Now, before I get to the temperature spectrum, I actually want to talk more about the polarization spectrum. And when we talk about polarization, remember that photons, we can describe the photon distribution function in terms of the Stokes parameters I, Q, U, and V. I is intensity, fluctuations in temperature. V is circular polarization. Because Thomson scattering does not generate circular polarization, but it does generate linear polarization. And that arises because if I'm looking in this polarization, photons coming in this way, scattering off of an electron coming towards you, this is the surface of glass scatter in this polarization. Photons coming this way, scatter to you in this polarization. When we talk about Q and U, just remind you that this is plus Q and minus Q, and this is plus U and minus U. I think I got the sign conventions right. And you can decompose the linear polarization always into to Q and U. What generates these fluctuations in temperature is primarily velocities at the surface of glass scatter. So if the material here is moving this way, that will generate a polarization this way. And the amplitude of the polarization signal Q plus IU is about equal to, it's a constant, turns out when you do the best fit by about 0.17, times the thickness of the surface of glass scatter, because the further you get to travel, the bigger velocity gradient you'll see, times a divergence term that's proportional to Q plus a curl term that's proportional to U if I've defined Q and U for a single mode. Because vorticity terms decay if we just have fluctuations in density, we only have, if they're just density fluctuations, only.
Why the curve was decay away?
Yep. We take the curl of this equation. This term is quadratic. Ignore it. This term, the curl of a gradient 0, the curl of the gradient 0. The force terms have a curl of 0. So we get something that looks like this. This was the Newtonian equation. If I do it relativistically, I have to write it like that, and the vorticity term decays as 1 over A. And you could also think of that as angular momentum is conserved. We have a rotating fluid, as the universe expands with the angular momentum being conserved, the vorticity decays away. That has a bunch of interesting implications, the fact that vorticity decays away. Vorticity is the source term for currents for magnetic fields. It also means primordial magnetic fields decay away. And we end up to linear order with only scalar perturbations. Okay, so...
Dissipation effects in that equation, like viscosity or anything?
Yes, so the viscosity terms, like the thermal gradient terms, are the ones that produce this finite thickness. So when we do the next correction and include the viscous effects, that's going to have the photons diffuse relative to the electrons, and that gives a finite thickness to this propagating shock. Now remember, we're always doing things actually in our actual calculations where we're keeping track of all of that because we're doing the full coupled equations. But in terms of your intuition, you can think of the photons diffusing relative to the electrons. Okay, so we write down this equation for Q, and you can see that the Q term is just proportional to div dot V. And if we look at the fluctuations, well, let's look at the behavior of the of those terms. Remember that delta dot is equal to IK V baryon. That's KV baryon, of course. Delta dot, the baryon fluctuations grow at some rate proportional to the Hubble constant at that time times the growth rate of structure. I'm defining F actually this way as the rate at which things grow. So the fluctuations we see in polarization are directly proportional to the velocity field at the surface of last scatter. So you can just think of the polarization power spectrum as the baryon velocity power spectrum. You're just measuring that directly. And in fact, we can take, and this is stuff that Chris Porto has been doing. There's a nice paper that Chris, a graduate student at Princeton, is running. This gets to the tests of gravity models. We can take our observations of CMB polarization and directly measure the baryon power spectrum at recombination. The baryon power spectrum at recombination is just proportional to the power spectrum of the E-modes in the polarization pattern. The E-mode patterns are the patterns that are mirror symmetric. They're the ones that correspond to the divergence terms. The B-mode patterns are the ones that are mirror antisymmetric. Those are going to be generated by gravitational waves. We'll talk more about those after the break. But the B modes are just proportional to this, actually divided by a bunch of constants that just directly from measuring the E-mode power spectrum. And the E-mode power spectrum observationally, this is something where being at the blackboard is a bit limiting because we have very nice observations from experiments like Planck that show the amplitude of the E-mode power spectrum as a function of scale, and this is sort of the amplitude on these different scales. This angle corresponds basically to this angular scale here. And these multiple peaks come from the fact that we're Fourier transforming a ring. If we were Fourier transforming an infinitely thin ring, the peak amplitudes would all be the same. Because the ring has a finite thickness, because of the effects of thermal viscosity and thermal conductivity, that finite thickness means the amplitude damps as you go to higher L. And by measuring the damping, you can measure the thickness, and the height is giving you the peak position and that angular scale. And the overall amplitude is telling you what the amplitude of fluctuations are.
Is this how you measure the thickness, or is there another way to measure it?
The thickness, this is one of the ways to measure it. You can also measure it by the amplitude, the thickness here. The ratio of polarization to temperature is going to depend on this delta tau squared. So we actually know the thickness to about 0.1% from the ratio of the polarization power spectrum to the temperature power spectrum.
Presumably you get more than just the thickness of the actual profile.
You get integrals over it. And if you change the profile, it will change the spectrum. So we have if you do something that has additional source, you modify the physics, for example, decaying dark matter, or dark matter that annihilates, that contributes at around a redshift of 1100, changes the ionization history, and that's going to propagate through.
If you want to compute it theoretically, the delta tau star, did you say it comes from fusion?
The delta tau star, the thickness of the surface of last scatter, comes from the duration of the history of recombination. So that's to do approximately, you do this calculation I did here. To do precisely, you need to look at the way recombination proceeds and propagate all these modes of hydrogen and helium.
So there is a precise formula.
There's a very precise formula, and people, these papers I mentioned do it. I mean, write down the equations precisely. There's precisely not an analytical solution. It has to be done numerically, but the level of numerical precision is better than 0.1%. There, multiple groups have done multiple codes. Yeah.
When in our readout from the EE spectrum, the power spectrum of the baryons, I mean, this tells me more than just the degrees of freedoms that are there. But what does it actually tell me about the states?
Well, so one of the things I want to stress that it tells you about is I can see what the baryons do at redshift of 1100. I can look at the large-scale distribution of galaxies, and that tells me what they're doing today. And I can take the ratio of the two, and this gives me the Green's function for how fluctuations evolve from redshift of 1100 to today. And this is actually a nice test of if we want to formulate an alternative gravity theory that doesn't require dark matter and ask what does that theory need to do to fit the microwave background. One of the things it needs to do, it has to get this correct from going from redshift of infinity to 1100. But it also needs to get right, because we just observed these two directly. This is what the power spectrum of baryons looks like at redshift of 1100. At redshift 0, it looks like these peaks are here, but they're much, much weaker. And you have to get from here to here. So you can just divide those two functions, get the Green's function. And the Green's function of alternative gravity theory has to have this very funny form where gravity goes positive and then negative and then positive and negative. And people write down theories like these modified gravity theories. And it's very popular to try to do this to fit galaxy rotation curves. And every now and then, lots of papers appear on AstroPH. They all do rotation curves. No one tries to fit the CMB. They always justify it by saying, modifying this is really hard. I don't want to do that yet, But the challenge is, we have these two observables. We can measure this ratio. You've got to do something really weird in your alternative gravity theory in order to fit at the same time our observations of E-mode polarization and large-scale structure.
eliminating dark matter.
If you're eliminating dark matter. Now, if you have cold dark matter, then we get to add another equation and watch how cold dark matter responds. And that's what I want to do in the next 10 minutes, is put dark matter in. And the dark matter evolution, as I said, is pretty straightforward. It just stays there. And the way I like to think about the dark matter evolution, because we care about things happening on superhorizon scales, is to, instead of looking at evolution in density fluctuations, to look at evolution in potential fluctuations.
So this assumes that there's not a photon for the dark photon, right?
If there's a megaphoton for dark photons, that just shows up as changing the photon power spectrum.
There was download of the sound speed for the dark sector would have included the
So you could So you can generate additional fluctuations in the. You can include other components. Actually, the one I should include first, just to show how that goes, is neutrinos, right? Because neutrinos can free stream out of these fluctuations. So if I want to do the calculation more accurately, I want to also keep track of how neutrino propagate. And they'll just, if I have an excess of neutrinos, they just free stream out. And neutrinos propagate out, and they actually move a little bit faster than the baryons and photons. And when I include the neutrinos, the neutrino fluctuations, I guess I've lost my perturbation equation, neutrinos have about the same energy density as photons. They're about 15% of the energy density of the universe at redshift of 1100. That acts on the baryon-photon fluid gravitationally. That shifts the peak a little bit, and shifts the peak positions. So the way in which we can constrain the number of neutrinos is by looking at the detailed peak structure. Something that was sitting on Adam Riess's slides is he said, well, if we add some extra relativistic degrees of freedom, we can shift the Hubble constant by about 2 kilometers a second per megaparsec. And what that does is that you can still be consistent with the data with about 3.3 or so effective neutrino species. So the neutrinos we know, plus another thing that decoupled earlier. And that increases the energy density in this component here. Another game people play, and there's a nice paper by Christina Kreisch, who is a graduate student working with me, so I should advertise the paper, that looks at neutrino-neutrino coupling. And what that does is make the neutrinos behave, not that they free stream, but as a fluid. That shifts the evolution of this neutrino component. That also shifts the peaks around a little bit. And if you add dark photons, again, you'll add something that you have to look at. And I think intuitively, the way to think about it is how does it propagate away? You know, think of its Green's function, how does it respond to the perturbation, and then you can see what happens here.
How do you distinguish at this level dark photons from neutrinos?
If they're just relativistic species not coupled to anything, matter, depends on how you want to formulate it. If you do that, then it affects the evolution of dark matter perturbations. But for the next 8 minutes, no dark photons. We'll just do ordinary dark matter, cold dark matter, and look at its evolution.
You mentioned that the modified theories of gravity address the velocity curves of galaxies,
Some do here, or attempt to.
but the cold dark matter is consistent with the velocity curves.
Yeah. Now there's interesting story about what happens in dwarf galaxies. That's a fascinating topic. It does very well on scale of larger galaxies. There are interesting discrepancies on dwarf galaxy scales, whether that is astrophysics, about star formation feedback, or telling us about the physics of dark matter, is a great topic for another talk. So let's look at the evolution here. So this is our fluctuations in photons and our fluctuations in dark matter. And we can look at the behavior of the potential fluctuations pretty simply. If we're looking at modes that are on superhorizon scales, so the wave number is less than the horizon scale at a given redshift, then on superhorizon scales, nothing happens. Phi is constant. If we look when modes enter the horizon, and when we're at redshifts where the universe is radiation dominated, then the energy density in the photon perturbations free stream, they smooth out. And the perturbations in the dark matter just stay there. They don't grow. So, I should have kept do this. The a squared's there. I'll multiply through by a squared. The energy density in dark matter goes as 1 over a cubed. This is constant during radiation domination, so that the perturbations decay is 1 over a, or if they enter the horizon at AH, they decay from when they enter the horizon to A equality during the radiation dominated epoch. If I relate this to conformal distance, this ends up going as conformal distance squared, and when I enter the horizon, means this goes as K equality over K squared, where this is the redshift at which I enter the horizon. During matter domination, things are again simple. If I go through my linear perturbation equations, I find that density fluctuations during matter domination grow as A. This all cancels, and during matter domination, phi is constant. So this lets us write down the transfer function for cold dark matter fluctuations. If they enter the horizon during matter domination, they just go from being constant during matter domination, during superhorizon scales, to constant during matter domination. If they enter earlier during radiation domination, it decays as 1 over K squared. I can then take this transfer function and ask, what is the power spectrum of galaxy fluctuations today? It's the primordial power spectrum times the transfer function squared, because this is a power spectrum is quadratic in the amplitude of fluctuations. The primordial power spectrum goes roughly as K, it's roughly scale invariant. The 0.97, the current best fit to data from Planck. There's my transfer function. So that says the power spectrum of dark matter rises as K, peaks at K equality, and then falls as K to the minus 3 at large scales. And at this point, I did this very rough calculation for dark matter only. Of course, I need to combine dark matter and baryons. The energy density in baryons is about 1/6 the energy density in dark matter, so it's a small correction. When you include that, these acoustic fluctuations imprint And the combined power spectrum has small oscillations on top of it. And large-scale structure surveys have detected these oscillations. And when people talk about using baryon acoustic oscillations to study the universe, they're seeing these small fluctuations on top, which have this characteristic scale embedded in them, and using them to measure distance to different redshift ranges. And this gives us the basic response of cold dark matter to the fluctuations. So I've hit 11. So let me stop now. After the break, we'll talk more about the temperature fluctuations and then say a little bit about gravitational lensing and gravitational waves.
Do all these things that you've been calculating, you can observations of CMB?
Yeah. Yeah, this is all what fits very well.